Hi guys, this is Logan and James with Northern Arizona Wind and Sun, and today we're going to go over some of the components that are involved in a typical off-grid solar system. So for most DC coupled off-grid systems, I think it really comes down to four main components. You'll have your solar panels, your charge controller, typically an inverter, and then the battery bank. So those are the main four items. Obviously there's a lot more that goes into a complete system besides just those pieces. So we're going to go over those big four components today and then touch a little bit on the in-between items, all the accessories and the other things that you need to make the system complete.
All right, let's start from the top. So typically an off-grid system is going to require, a sustainable solution is going to require some solar panels. In the industry, nowadays, most panels tend to be, or at least the most cost-effective panels tend to be 60 cell or 72 cell panels, or 120, 144 cell. They're pretty much analogous. Your average 60 cell panel, regardless of whether it's poly or monocrystalline, it's going to be about 66 by 40 inches, right? Mm-hmm. And 72 cell or 144 cell panel is going to be around 80 inches by 40 inches. A typical 60 cell panel, your range probably somewhere between 300 and 330 watts, I guess it's safe to say. There's some models that are much higher output, really efficient panels, but your average monocrystalline module is going to be somewhere between that 300 and 330.
Right.
72 cell, what would you say?
Maybe 360 and upwards these days.
For monos? Yeah, I would say so too. Anymore, we find ourselves most commonly using monocrystalline modules. Anymore, the only difference between them is, besides performance, it's really just cost. Mm-hmm. And most manufacturers have for the most part, kind of done away with polycrystalline. They're falling out as far as availability is concerned, right, or practicality. The cost difference is really what pushed poly in the early days, because they were so much cheaper to make. But anymore, they're almost come in line with each other. So there's really not an advantage to using polycrystalline anymore.
Right.
So we find ourselves doing mono.
Mm-hmm. Yeah, for the most part, the panels nowadays would be a monocrystalline panel. Now, when he's saying a 60 cell and a 72 cell, he's literally referring to the individual cells or squares that make up the panel. So not only does that kind of touch on the panel's construction, but we tend to use those terms when we refer to kind of a standard or an industry standard size panel. So
yeah, because it determines the amount of cells, determines the voltage, the open circuit voltage, the rated voltage, the power output. So knowing what panel you're using helps us determine, the limitations of a given configuration, which sort of leads you to essentially like the wiring and the overcurrent protection and the way we combine strings. So if you have most common, so we're talking specifically about DC coupled off-grid systems. So with those kinds of systems, you'll have an array which is made up of multiple modules. We just touched on modules, right? Modules, right. 60 cell, 72 cell. That's the specific one unit is called a module. Mm-hmm. Then they're configured in series parallel configurations to create what's called an array, and then we deliver that. So your average array configuration is going to be something close to 3 to 6 panels in series for a typical DC coupled system. Mm-hmm. There are some cases where you can do 600 volt strings with upwards of 12 or 13 panels in series.
Right.
But generally, most DC coupled applications are going to be 3 to 6 panels in series. Mm-hmm. And each string, 15 amp?
Yeah, no more than 20 typically.
No more than 20 amps.
Right.
We'll combine them in a combiner. This will be your string level overcurrent protection as well as leading into a home run, essentially.
Right.
Before we get too far off of the actual array, let's talk about the ways you would mount an array, right?
Correct. So there's a whole number of different ways you can mount your panels. Obviously, you're not just setting them on the ground or leaning them up against your home. You need a way to secure them and make sure they don't get blown away or damaged in any way. So this is really application specific. So I'd say for the most part, there's maybe 3 main mounting methods that we would usually use for a system like this. For mounting the solar panels, it could be on the roof of a home or a structure. You can put the panels on a pole. And then the third most common method would be a ground mount, where you have kind of the panels laid out, typically with multiple piers or pipes coming out of the ground, and the panels kind of sit on that. So
one of the most important considerations with the roof mount structure anymore now in this day and age with the current National Electric Code requirements is going to be rapid shutdown requirements. So you're going to want to find out if you're doing a permitted application, what your authority having jurisdiction is going to require, what NEC, National Electric Code standard they're following, and make sure that you're going to be compliant with any rapid shutdown requirements. There's a lot of ways to do this. Mm-hmm. You can have individual module level rapid shutdown for NEC 2017. Right. Or array level rapid shutdown for NEC 14. Mm-hmm. Also, ground fault detection is really important. Arc fault detection,
correct,
is very important. If any conductor enters a structure, you have to have arc fault detection. You have to have ground fault detection on all arrays. Mm-hmm. A lot of charge controllers have this built in. We can touch on that in a minute. I think that for the most part summarizes your typical array. Combining an array together and sending that home run to the equipment that manages the power from the array is the next topic.
Right. So just to kind of review, typically you would have multiple groups of solar panels wired in series, and then the various groups would be combined in parallel. So you're bringing all these individual groups into a central location, which would be your combiner box in most cases. And then out of the combiner box, now we're condensing all these different groups and wires from the array. That's being condensed now into a single positive and negative cable, and then that would run back to the rest of the equipment. Once we've taken care of the solar panels, the array wiring, our mounting hardware and all that, the next main component in our system will be the charge controller. So the charge controller is the device that manages the flow of energy from your solar panels to your batteries. In other words, it makes sure your batteries get charged properly, and it makes sure that they do not get overcharged, which is very important. So in the world of charge controllers, there's 2 main types. One of those, which we most commonly use, would be the MPPT version, and that stands for maximum power point tracking. The other type of controller you'll find out there would be a PWM type controller, and that represents pulse width modulation. So I'll let James go over a little bit the differences between those 2 controllers and why one might be a better fit for your application than the other.
So let's start with PWM, pulse width modulated charge controllers. So your PWM charge controller, effectively, when you use one of those, you want to have the PV array matched to the nominal voltage of the battery bank, because essentially what that charge controller is doing is it's connecting the panels directly with the batteries. When in a bulk charge, we probably won't touch too much on the various states of charge, but when in a bulk charge, the charge controller is trying to get as much energy from the solar array as possible. It's directly, the PWM charge controller specifically is directly connecting the array with the batteries. When your batteries get to a certain constant voltage set point, we call that a CB set point, then essentially the PWM charge controller starts to limit current to the batteries by pulse width modulation. So effectively it's effectively turning a switch on and off in various frequencies to limit how much power goes into the batteries, right? So that's where that PWM comes from. And so in that particular configuration, it's really important to note that the nominal voltage of the panel needs to be the same as the batteries. If it's a 12 volt, it needs to be a 12 volt panel, 24 needs to be a 24 volt panel. It's pulse width modulating to limit current. There's not a whole lot of control over the power that you get from the modules or how the charge controller is kind of receiving that power from the array. It's just dump it into the batteries. An MPPT, it's a maximum power point tracker. So that's essentially what it's doing, right? It doesn't matter what panel you use, provided the input voltage is about 30% over the battery voltage, up to the limit of the charge controller. There's various charge controllers with various input limits, but essentially a maximum power point tracker is effectively tracking the maximum power point of the array. It's sweeping the power curve, and it does this. Every manufacturer has a little bit of a different algorithm for how they do it, but essentially it's sweeping the maximum power point of the array, finding the point at which it can get the most power from the solar array, and it's pushing that into the batteries. An MPPT charge controller is essentially a buck converter. It's just taking a high voltage input, lower current input, given amount of power, converting that to a lower voltage output with a higher current for the same amount of power. It's basic Ohm's law with a little bit of efficiency loss mixed in between, but essentially it's a buck converter. And so with the ability to do that, it can also very accurately control how much power it delivers to the battery bank as well, which is really important when batteries get full and you're trying to satisfy loads from the inverter or from DC loads. So that's basically the differences between them. Essentially, with a PWM, you have limited PV input compared to that of an MPPT. You'll have the ability to capture the most power from the solar array at any one moment. It's possible for a PWM to produce as well as an MPPT, but it's never possible for a PWM to produce better than an MPPT if the array is delivering into that MPPT correctly.
Right.
That's safe to say?
I think so. At this point, most newer designs especially would have an MPPT controller. There are select applications and instances where a PWM might be a better fit, but typically if we're designing a new system from the ground up, it'll be an MPPT controller for the most part. So one side note about the charge controllers, and this again is a little specific to the application and what's going to be required per code or per your inspector, is arc fault protection and ground fault protection. So depending on the model of the charge controller, those features may very well be integrated already. They might be built into the controller itself. So at that point, you don't need any extra, you don't need to do anything extra to satisfy those requirements. If we're using a controller without either of those protective features and you do need arc fault or ground fault protection for the system, there are other ways to integrate that, whether it be a certain combiner box, whether it be an external circuit breaker or arc fault protective device. So obviously that's something we can advise on depending on what you need for your system.
Just bear in mind that most off-grid applications, especially permanent off-grid applications, are going to require ground fault detection. Well, just about all will require ground fault detection, and most will require arc fault detection.
Right.
And so having a charge controller with that built in saves you the need to have to do it, externally. There's options. We can definitely help with that.
Exactly.
And help with advising the best choice based on the cost and convenience of installation.
Right. So moving through our little list here, we've hit the solar panels, the charge controller, and then now the next main component we'd have in an off-grid system like this would be your inverter. So for almost every off-grid system, the inverter is a battery-based inverter, and for the most part, what the inverter does is it's taking DC energy that's stored in your batteries and it's changing that to usable AC power and sending that to your loads. So just like you would plug an appliance into an outlet in your house that requires AC power, that's basically what the inverter is providing for us in an off-grid situation like this.
Important considerations are like what you need for your AC loads, right? So you're going to have AC loads that are 120 volts are given with the US applications for sure. We do a lot of foreign applications as well with need for 230 volt or whatnot, but generally here in the States you're going to need 120 volts from the inverter. The real consideration is whether you need split phase configuration, which is 240 volt. Do you have 240 volt loads like a dryer or a 240 volt well pump or an air conditioner? These are common loads that could be 240 volts, and that's going to dictate which inverter is ideal for your application. Right.
And then in terms of sizing the inverter, that's when we take a look at what you're actually wanting to run or power, and more specifically, everything that needs to be on at the same time. So you have to think about the different appliances or loads you're going to be powering all at once, add up all those wattages, and that gets us in the ballpark, at least gives us an idea of how much power that inverter needs to be able to supply.
Well, we did a video on how to do a load evaluation. So it's very important to know what your loads are. You can watch that video and it'll tell you exactly how to do that load evaluation and why we kind of need to do that load evaluation to determine what inverter is best for your application.
Right. So one thing that's specific to the inverter is usually its DC input voltage, or in other words, the battery voltage. So an inverter that's battery based is almost always going to have a fixed input voltage. So what that means is that if you have a 12 volt battery bank, you need to have a 12 volt inverter.
Yeah, a 12 volt inverter won't work on a 24 volt battery
exactly.
bank. And a 24 volt inverter will not work on a 12 volt battery bank. And most reputable manufacturers don't offer one that's flexible.
Correct. So unlike our solar charge controllers, which can be configured on really any battery voltage, the inverter's battery voltage is fixed. So that cannot be changed like the charge controller's voltage.
And it often defines what you're stuck at.
Yeah.
Right? Unless you want to invest in a new inverter. So when choosing an inverter, it's really important to choose a battery voltage that's either going to allow you to get the system to where you want it to be in the future if you're planning on doing expansion. So these considerations are really important to make, and we can help you with the recommendations for that. That's one of those decisions you don't want to rush into a particular inverter, because once you're stuck at a 12 volt, like you're either investing quite a lot of money in a new inverter to get up there, or you're stuck at 12 volt, and there's some serious limitations with lower voltage battery banks. So,
since the inverter would be fixed at a specific battery voltage, like James was saying, it really is it's an important decision. You don't want to rush into the inverter, picking the inverter at least, or at least the voltage of the inverter maybe more specifically. That is definitely something you want to decide on in the initial planning stages of your system design. So the inverter is almost one of the first things that we would select, and then we can kind of build most of the rest of the system around that. Staying on topic with inverters, for a lot of our off-grid systems, we tend to use an inverter charger.
I mean, it makes the most sense.
Yeah. So
when you're off-grid, you need redundancy. So I'll let Logan explain what an inverter charger is, and then explain why you need it so much.
So we know what an inverter does. It takes DC out of the batteries, changes it to AC to provide power to your loads. So an inverter charger retains that exact same functionality as the inverter does, but it also doubles as a battery charger. So what that means is that an inverter charger has an output, but it also has an input. So on the input of an inverter charger, you'd be able to connect things like a generator for most people who are truly off-grid. You could also run power from the grid, if you did have electricity at your property, into the input of an inverter charger. So when the inverter charger sees an external AC source present, it's actually totally changing its mode of operation.
It's literally running in reverse.
Right. So usually the inverter is pulling energy out of your batteries. It's discharging the batteries to power up your loads. If you turned on your generator, or if you did have grid power potentially at the property, now that inverter sees that external AC source and it thinks, well, I have this other source of energy, let's stop discharging the batteries. So what happens is now it takes that external AC power and it starts pushing it through to your loads. And now whatever's left over,
it's a direct pass-through.
Mm-hmm.
There's a transfer switch in an inverter charger that transfers. It stops inverting, passes power through to the AC loads.
Right. And then whatever's left over after your loads are taken care of and happy. Now, if there's still excess AC power coming through on the input, that is used to charge the batteries. So typically with an inverter charger, in an off-grid situation especially, that external AC source is almost always a generator. And like James was saying, very, very good idea to have redundancy in your system. If you have several cloudy days on end and maybe the batteries are low, maybe our solar panels aren't quite keeping up, you definitely want to have that generator as a backup just in case. And then basically at that point with the generator on, you're powering all of your AC loads and then typically charging the batteries at the same time.
Yeah, it's an important thing to have.
Yeah.
So that I guess that leads us to batteries.
Yeah, and so now the last main component in the system here would be the actual batteries themselves.
Probably one of the most important considerations.
Absolutely.
Too. It's definitely one of the most expensive aspects of a system,
Mm-hmm.
and it's the most challenging to set yourself on.
Right.
There's a lot of options. Generally, in our industry, we kind of use 2 different chemistries for the most part. There's others, but most commonly 2 different chemistries. So we're going to have lead acid chemistry or lithium, which is becoming more popular. So with lead acid, there's several options.
Right.
They're not different chemistries. It's still the same chemistry. They're just different ways the battery is manufactured, assembled
Mm-hmm.
to some degree. So you have flooded lead acid batteries, which are one of the most common. And you have AGM, and then you'll have gel. So, I'll let you explain a little bit about flooded battery.
Sure.
And then I'll kick in on AGM.
So a flooded battery is your typical standard lead acid battery, wet cell battery. Those are usually almost always the most cost-effective option up front anyways. The batteries themselves are fairly inexpensive, but there's maintenance that comes along with a flooded lead acid battery.
Important maintenance.
Right. So in order for you to keep your batteries healthy and actually get a decent lifespan out of those type of batteries, you do need to be very regular with the maintenance. So when I say maintenance, that's involving things like adding water to the batteries.
Checking the electrolyte level
Right.
within the battery, checking specific gravity,
Right.
Assuring the battery is actually fully charging.
Mm-hmm.
I mean, these are some of the considerations that if you don't make while with that type of battery, ultimately it'll get destroyed. So you want to make sure that you're regularly checking the water level so that it doesn't run dry, the
Right.
blades don't get exposed. You want to make sure and check the specific gravity so that you can confirm that you're correctly charging the battery. Again, those are things that will reduce the life of the battery over time.
Right. Yeah. Regular equalization charges as well are usually involved when you have a flooded battery.
So reduce stratification.
Yeah, exactly. And what that means is just essentially a controlled over voltage charge to your batteries to make the electrolyte agitated and break up all the gunky buildup that can occur on the plates. So in other words, it just keeps the batteries happy, it keeps them operating efficiently. One of the
Oh, go ahead.
one of the biggest considerations, I think, for a flooded lead acid battery comes into play with ventilation.
Yes.
So there are certain situations when the batteries are charging when they will off gas hydrogen, and if you do not have these batteries in some kind of an enclosure or outside potentially, or at least with an active ventilation solution to push those fumes away from your equipment, you could have a very bad and dangerous situation on your hands. So that's absolutely one of the, I think, most important things to think about is for flooded batteries, that is where we're keeping the batteries and how we're dealing with the hydrogen buildup.
I mean, aside from that, you also have the possibility of spilled acid and stuff like that.
Correct.
So to consider. But flooded batteries are probably the most cost-effective upfront battery solution. So if the maintenance is not an issue to you, if you do regular oil changes and you keep up with your equipment and you feel confident keeping up with the lead acid batteries, then probably a perfect solution for you. We do find a lot of people that are just getting into off-grid tend to burn through their first set of batteries pretty quickly, unless you've kind of generalized the understanding of the maintenance. But the most cost-effective upfront solution takes us to one of the next options, which is a maintenance-free solution. So AGM batteries. We do a lot of systems with AGM batteries. AGM is an absorbed glass mat battery. Effectively, the electrolyte, rather than being in a liquid form, is absorbed into a fiberglass mat between the plates. So we call these valve-regulated or recombinant batteries. So they're completely sealed. There's really no maintenance to them. There's not a lot you can do as far as seeing what they're doing, right? So you can't confirm they're fully charging by checking specific gravity. You really shouldn't equalize them. You can do what's going to conditioning charge, but generally you don't want to push those batteries too hard like you can with a lead acid battery, because ultimately if you do gasify them to a concerning degree, then you'll pop a valve and it'll lose. So, but AGM batteries are along the lines as they're still lead acid configuration. They still have similar characteristics to lead acid, flooded batteries specifically, but they're maintenance free, and so the same considerations that you would make with a flooded battery, besides the maintenance, are still there. So
So in terms of your efficiency, your performance, your lifespan, the amount of cycles you're going to get, even physical size and weight for that matter, all of those parameters are going to be pretty similar between a flooded lead acid battery and a sealed lead acid battery. So again, the big advantage or the main thing that sets apart a sealed battery or an AGM battery from a flooded is the maintenance issue. They're totally maintenance free. For that reason, because they don't require you to constantly look at the water, specific gravity, equalized charge, etc., an AGM battery is going to be a little bit more expensive than your flooded battery if you're just getting started. So,
but you have less risk of destroying it.
Correct.
By not maintaining it.
Right.
Then again, there's still ways you can destroy them.
And that's maybe one of the disadvantages potentially in an AGM is if you abuse it or mistreat it, there's not really a whole lot you can do to revive the battery or bring it back in a sense. Whereas with a flooded battery, if you do mistreat it or abuse it or over discharge it, what have you, sometimes you can, do an equalized charge to boost the efficiency back up a little bit, and that can help maybe get you some extra life out of the battery, whereas you can't necessarily do that with an AGM.
So we can talk briefly about gel batteries. So we don't commonly use gel in this industry. There's some limitations on how quickly you can charge them, how quickly you should discharge them. I guess it's how quickly you should. There's some negative effects that can come about by charging them too quickly. commonly used in telecom, low discharge, long charge applications. But basically, instead of the electrolyte being stratified in a fiberglass mat, it's in a silicon gel. So it's still a maintenance-free solution, valve-regulated, recombinant, but again, there's some limitations, and we typically don't recommend them for off-grid applications with possibly high current discharge and charging, especially with solar.
Right.
With solar, you really have to get that energy back into the batteries quickly in order to get them fully charged for the next night.
Right.
So gel batteries don't like that as much. So.
Right. So for our purposes, for the most part, we would be using an AGM battery if it was a sealed lead acid or a maintenance-free lead acid solution.
Makes the most sense.
Right. So that was a little brief bit about the two different lead acid-based chemistries. Now the third one we'll talk about today would be a lithium battery. More specifically, lithium iron phosphate is the chemistry. Now, the lithium battery is significantly different than the previous two types in a number of different ways, not only in terms of its physical specification, size and weight, etc., but how it performs, where the voltage sits, how you can use them, charge them and discharge them, etc. James is, I would say, maybe our in-house lithium expert, so I'll let him go over some of the specifics and the advantages of that battery type.
Well, okay, so first things first, lithium is an ambiguous term. Everyone says, oh, I want a lithium-ion battery. It's really important to specify the chemistry. So lithium-ion is a generic blanket term for any lithium chemistry, and there's like 6 or 7 common chemistries or mixtures of chemistries on the market for various applications. It is, I guess, each chemistry for that lithium battery has its advantages and disadvantages. In this industry, we most commonly use lithium iron phosphate chemistry or lithium ferrophosphate, whatever twist you want to put on the actual chemical composition of the electrolyte and primary elements. But the important considerations to make with that chemistry is that it's an extremely safe, non-volatile chemistry, unlike other lithium chemistries on the market, and it is designed specifically for like a significant amount of cycles. Right. So it's non-volatile, high cycles. That's what makes it super advantageous for these off-grid applications. Side note is that they tend to have, or I guess the slight disadvantages of that particular chemistry against any other lithium chemistry is their energy density is a little bit lower, which doesn't so much matter for an off-grid application. We're not trying to fly with these things. So it's not a big deal. Their nominal voltage tends to be a little bit lower than other chemistries, but which is an actual advantage in some degree. So needless to say, that's the specifics for that particular chemistry against any other lithium batteries. I guess what's important to touch on at this point is that lithium iron phosphate chemistry, it lines up fairly similar to that of like an AGM battery as far as its charge and discharge voltages are going, with the configurations. So in a 12 volt application, they're typically 12.8 volts nominal. On a 24 volt application, I think they're like 25.6. And then on a 48 volt application, they're 51.2 or so volts. So those are the nominal voltages of the battery bank. Being that the nominal voltage is slightly higher than that of a lead acid, we find that the full discharge voltage is going to be right around 12 or 24 or 48. Right. So that's completely empty. And the full charge voltage, again, is going to be somewhere close to what you would see on a typical AGM battery. And it's going to be specified differently for each manufacturer.
Right.
But the range of voltage works perfectly with your typical lead acid battery. And that also kind of leads me to, if the equipment that you're using or you intend to use can work with custom battery configurations, then chances are you can configure that equipment to work perfectly fine with the lithium iron phosphate chemistry.
Absolutely.
That's a really important consideration.
Yeah.
So, what other advantages do we have here with lithium?
Well, I'd say one of the biggest features maybe about the lithium batteries, most of the lithium batteries we deal with, is almost all of them have an integrated battery management system. So that's referred to as a BMS for short. So every single individual battery has a BMS built into the battery itself, and that BMS is constantly monitoring the battery's surroundings. And so what the BMS does is, if you abuse the lithium battery, or if you mistreat it, if you discharge it too far or charge it too much, or it's too hot or cold, etc., that BMS can recognize that its operating parameters are being exceeded, and the BMS will actually force the battery to shut down until that condition is resolved.
It's a protection.
So it's a level of protection on the batteries, which, in my opinion, I think it makes it a bit hard to abuse them or damage them, because if you do anything wrong to the batteries, they're going to shut themselves down before any negative impacts can really set in or occur.
That could be an inconvenience, but it's not
Correct.
Detrimental to the overall system performance.
Right.
So you could recognize the issue, resolve the issue, carry on without any major effects. If you did something bad with the lead acid battery, it could almost be immediately detrimental to the battery bank. So they're protected in that manner. In the BMS is looking at individual cell level voltages. With a lithium battery, mind you, the BMS is going to prevent this from happening, but with the lithium battery, there's not a whole lot of forgiveness. If you over discharge a given cell beyond its minimum discharge point, it'll be completely destroyed. If you overcharge a lithium cell, bad things happen. So, that BMS is constantly looking in there and making sure that everything is within spec. If anything gets out, then it's going to force the system down and, keep you from destroying that battery.
Right.
So, it's also, in most cases, lithium batteries are done at the nominal voltage of the battery bank. So this kind of stems back to picking the right voltage for your inverter. If you guys are picking a 24 volt or a 48 volt solution, you get a lithium battery at 48 volt. You get a lithium battery at 24 volt.
Right.
And they're configured in parallel configurations, so you can stack them like Legos, just build upon them. That's actually one of the most significant advantages for a lithium battery bank, is that you can start with a battery bank of a given size, and you can add to that battery bank over time. This is one of the considerations that you would not want to do with a lead acid battery. Negative results from adding batteries over time to a lead acid battery result in failure to that battery bank, premature failure. Whereas a lithium battery bank doesn't really care. They're parallel circuit, and basically each battery is charging and discharging on its own, but contributing to the end, right? So they're less affected by one another's various attributes or characteristics or age degradation.
I would say that because most lithium batteries are already at your nominal system voltage as is, they're all being connected in parallel. So not only is that allowing current to enter and leave the batteries nice and evenly, but it also does build a little bit of redundancy in your system too. So if you think of a typical lead acid battery bank where maybe you have 8 6-volt batteries all in series to make a 48 volt bank, well, if you lose one of those 6-volt batteries or it gets damaged in some way, you can't make 48 volts anymore. So now your system is basically offline until you get another 6-volt battery and bring your system voltage, or your battery bank voltage, back up to 48. With a lithium battery bank, if you have multiple batteries in parallel, for whatever reason, if you did lose a battery, if one went offline, if you needed to move it, who knows, you can still keep your system online. Now, granted, you may need to reduce some of your loads and some of your charging to make sure you don't exceed any current limitations if you're reducing the amount of batteries in your bank. But because the lithium batteries are already at our nominal system voltage, losing one battery out of a bank, that doesn't necessarily mean you're forced to shut your system down.
Right. Just carry on.
Right. So, I mean, aside from that, they're, I would say, superior to any lead acid chemistry in a number of different ways.
Efficiency.
It's
like adding a turbocharger to your system.
Exactly.
It's like, cycle rate, life, warranty. I mean, most of your lead acid batteries are going to be warranted for 2 to 3 years, although it's very rare for you to have a failure due to warranty. Most of the time the failure is due to abuse. But in the case of lithium batteries, almost all reputable manufacturers are warranting them for about 10 years.
Right.
Something between 6,000 and 10,000 cycles is what they're expecting. Depth of discharge.
Yep.
So with lithium batteries, most lithium batteries aren't going to be rated in amp hours like a typical lead acid battery. Although they are, being that their nominal voltage is different than a lead acid battery, it's not fair to compare them to a lead acid battery's amp hours, and their usable capacity is considerably more. So an apples to apples comparison with lithium batteries is tough because you need to consider all aspects of performance and what the system's doing.
So you can take a lithium battery down to a 0% state of charge. You can use 100% of its capacity, because once it gets to its limit, the BMS takes over and it's going to shut that battery down to prevent any further discharge. A lot of the manufacturers we offer for lithium batteries, they do recommend an 80% discharge limit. That still gives you quite a bit more usable capacity than most lead acid batteries.
It's primarily to extend life.
Yeah.
It's not a requirement, but it's there to
helps to maximize your cycles.
It's the break-even point.
Right.
The other thing to consider with lithium batteries is they can deliver a ridiculous amount of power compared to that of a lead acid battery bank continuously without suffering reduced capacity, and they can charge really quickly.
Right.
So we do a lot of remediation systems, generator remediation systems, where charging the batteries extremely quickly is the goal, so you can save fuel. Or if you just want to, oversize your solar array so that your, heavy loads, air conditioners and stuff like that are running during the day. You want to get those batteries charged quickly and carry on the loads, like not off the batteries. These applications where you have really large charging systems, the lithium batteries can tolerate that. So not only can you do a smaller battery bank, but you can do your charging much quicker.
Right.
And coupling that together without negative effects from that are one of the significant advantages of lithium batteries.
Right. And then I'd add as well that because the lithium batteries are so much more efficient, because their energy density is higher than a lead acid, very, very often we are helping people upgrade an existing battery bank with lead acid to lithium. So I would say in most of those cases, you're usually reducing the overall quantity of batteries in your bank.
And the physical size of the bank.
And then, not to mention freeing up a whole bunch of area. The weight of a lithium battery, equivalent capacity more or less, is going to be a fraction of that,
like a quarter
of a big lead acid battery. So much easier to move around, much easier to transport and install. You're freeing up area in your solar room or wherever your equipment's housed, and
there's one other consideration I don't think we specifically touched on, but it probably would have been important to mention this from the very beginning, is that lithium batteries are completely maintenance free.
Yes.
Like there's nothing you can do to them.
Yeah. So just like our sealed lead acids, our AGMs, our gels, the lithium batteries do not require any maintenance whatsoever.
And one of the other significant advantages of a lithium battery compared to that of a lead acid is that they do not need to be fully charged.
Correct. Yeah, I was going to add that as well. They do fine in a partial state of charge environment, whereas any lead acid battery, your goal is really to fully charge those batteries every single day, or else over time that deficit cycling, that lack of a full charge in a lead acid battery, it really does start to show, and
it's going to build
hurts
up
your performance.
Yeah, irreversible damage
Right.
eventually.
Right.
So I think that pretty much covers everything.
Think so?
Quite detail. If you have any questions regarding any one of these specific topics, or if you want more detail, feel free to give us a call, shoot us an email, leave a comment. We can create a video on a specific topic in greater detail. Visit our website. Again, give us a call. We'd love to talk to you guys.
Thanks for watching.
Thank you for watching our video. If you enjoyed it, please like, subscribe, and comment.